So first of all, I want to thank the organizers for selecting our paper and the reviewers for selecting this paper. So this is a work motivated by a problem in multi-class classification, which is that the outcome labels may be ambiguous. So to address this problem and to provide some data-driven guidance for combining ambiguous labels, we propose this criteria called Information-theoretic classification accuracy, short as ITCA. So our motivation is that when we do multi-class classification as a prediction problem, the data quality may be a concern. And the outcome labels, like different classes, may be ambiguous due to maybe subjective labeling and also inconsistent labeling by different labelers. So we were motivated by this application from our medical collaborator at UCLA. So he's a neurosurgeon, Maxim, and he wants to study this TBI, traumatic brain injury patient care problem. So the question is, after the surgery, which patients should we send to rehabilitation centers or keep them longer in the hospital? This will matter for the medical efficiency and also the medical resource in the hospital. How can we optimize the patient assignment? So to address this problem, we want to be able to predict a patient's rehabilitation outcome from the patient's admission features. We want to know which patients will benefit the most after being sent to the rehabilitation center. So we have historical data with patients' admission features and their rehabilitation outcomes. However, the prediction accuracy is low. We want to predict a nominal 7 levels as the outcome. And a primary reason is that the labels are arbitrary, and they were labeled by different graders. For example, level 3 and level 4 may not be so different. So the question is, can we combine adjacent ambiguous outcome labels to achieve better prediction accuracy? So there's some related literature in the classification topic. So people have developed methods for classification in the presence of labeling noise using a robust loss function or using ensemble learning, or to just remove data points that are likely mislabeled, or using data generative models to model data noise. And another category of literature is called set value prediction, like conformal prediction, which will predict a set of class labels instead of just one class label for each observation or instance. Or there are people who design their utility function to maximize, to do set-based prediction. This is from the economics literature. However, all these existing methods do not guide global class combination. So for the first class, they just consider the noise, but they don't consider the combination of all the class labels at the global level. For the second type, they will predict a set for each instance, but it's not global combination. So therefore, motivated by this gap, we want to find something to find a trade-off between classification accuracy and resolution. So clearly, we can boost the accuracy to 100% if we just combine all the class labels into one. This is a naive solution, but clearly not what we want. So how can we find the trade-off between accuracy and resolution? And we want first we want a method or criterion to characterize the resolution, because we don't have a way to quantify it yet. And second, given we can measure the resolution, we want to balance the accuracy and resolution. So motivated by this, we propose the ITCA. So our idea of measuring the resolution is from information theory, the entropy concept. So we consider these two ideal scenarios. First, if all the classes are balanced, they have equal proportions. Once we increase the class number, the entropy increases, which is about the entropy of the distribution of the outcome label. And second, if we fix the number of classes, but change the class proportions from the very unequal case, like one class dominates, to the equal case, all the classes have the same proportion, we can also see the increase in the entropy. So because of these two considerations, we think entropy of the class label distribution, it offers a natural way to measure the resolution, because we want to say that the more classes, the better resolution, and the classes, if they're more even, the resolution is better. So this is the notation we use to formalize our ITCA. We consider this class combination map from the original K0 classes to a smaller number of K classes. So in this case, we can have this map in this example as combining 4 classes into 3. And we combine classes 2 and 3 into one class. So we also denote the inverse of the map as a set, right? So the new class 1, original class, the pre-image is set 1, and the new class 2 has the original classes in the set as 2 and 3. And a pre-image of the new class 3 is the original class 4. So we can have the inverse. We need those notations. So then with this class map notation for class combination, given the training data, we denote it as DT. T stands for training, a classification algorithm to be trained on the training data, and the class combination pi k. So the subscript k indicates the number of classes after the combination. We can have a classifier denoted as phi pi k in the subscript, and C algorithm and DT training data in the superscript. This is the notation. So once we have an instance with X feature vector xi and outcome label yi, we can actually use the training data to train the classifier. And for a new instance, we just input the feature vector x, and we want to predict the y. And this y will be one of the k class labels after combination. So a natural way to think as a start point is to think about the out-of-sample accuracy, which is commonly used for evaluating a classifier. So suppose that we have this classifier, we apply it to the validation data, denoted as DV. V stands for validation. This is the out-of-sample accuracy. We just calculate the proportion of validation data points that are correctly predicted. So note that for this validation data point, we apply the class combination. So we're evaluating whether our prediction is correct given the combined class label. Okay, so we can rewrite this formula as the summation over the number of combined classes, k from 1 to big K. And in this reformulation, we actually have it as the conditional accuracy in the kth combined class multiplied by the kth combined class proportion in the validation data. So this is just a notation for the proportion. So it's a proportion times conditional accuracy, and we sum over combined classes. But you can see that this accuracy will be dominated by the majority class in the validation data. If one class has a very big proportion, then its conditional accuracy will determine the accuracy, and which is not what we want. So motivated by this traditional criterion, we modify it by changing the proportion of the kth combined class by the resolution we define, which is the contribution of the kth combined class to the entropy of the class label distribution after combination. So this p, it becomes negative p times log p. That's the contribution part of this class. And we can see this formula, ITCA, in 2 ways. First, as an entropy weighted out of sample prediction accuracy. The weights are changed to the entropy. Or we can see it as another way. It's the accuracy weighted entropy formula. So it has 2-way interpretation, and you can see it has a trade-off, right? Entropy for resolution and accuracy for that class. And this one shows that compared to the traditional weights in the accuracy, which are class proportions in the blue bars, the new weights in ITCA can overweigh the small classes, minor classes, and underweigh the major classes. So it achieves better trade-off, balance of those classes, and to make the ITCA criterion not dominated by the major classes. And another nice aspect of ITCA is that we can see it in this alternative definition. So by rewriting the formula, we can take the summation over the data points or instances in the validation data instead of summing over the combined classes. And so we can actually see this interpretation for the ith data point. If we don't know which class it belongs to without knowledge, the entropy should be the points distribution in the uniform interval between 0 and 1, because we just divide the interval by the class proportions. So we're using 5 original classes, 5 combined classes as the illustration. So the entropy is 0. But once we know this point belongs to class 3 after combination, then the entropy is only for the points distribution in class 3, and we can calculate the entropy as log P3. And the difference, which is the reduction in uncertainty, becomes negative log P3. So looking at this formula, we can actually see that if we do the prediction correctly for the ith point, we can have this amount of reduction in our uncertainty. And that's our ITCA. So ITCA just basically measures the amount of reduction in uncertainty after we predict the validation points correctly. So I will skip the other 3 alternative criteria we also consider based on our thoughts to balance the resolution and accuracy. But these 2 are not our proposals. Common use criteria, one is the accuracy I mentioned, the other is the mutual information commonly used for evaluating clustering. So we also compare against these 2. So there's an iris data set many people have used before in their classes. So it has 3 classes of flowers. We use this example to show that if we randomly divide one class into 2, and ITCA does the best job for identifying the correct combination, like which 2 of these 4 classes should be combined into 3 classes. That's the ground truth. So ITCA does the best because it has the maximum at the correct ground truth combination, and it has the largest gap between the ground truth and the second best combination. And back to my motivating example, that TBI patient treatment, we actually see that with our ITCA combination, we can have the best increase in terms of accuracy from the best guess. The best guess means that given the number of classes, I just guess my patient to belong to the largest class. That's the best guess. And we know that if we combine the classes, the best guess accuracy will increase. So we use the best guess as the baseline, and we can have the best improvement in accuracy. And we also have the experts combination labels for each outcome, like toileting, grooming, but the experts label is not specific to each outcome. It's just one combination of the 7 levels into 4 levels. So we see that for grooming, we agree with the expert, but for the other cases, we can do better than the expert labels. And also, another use of ITCA as a criterion is that we can build this hierarchy to combine the 7 classes consecutively into fewer classes. And we can decide the order of combination to maximize the ITCA in each step. And we can allow for the greedy search or nested search or the exhaustive search. So, and we can tell you which combination maximizes the ITCA, so where to stop. Another application is to the single-cell RNA-seq data cell types. So we apply it to this Hydra data published in Science, and it has 38 cell types. We want to decide whether some cell types are ambiguous and should be combined. So one notable result is that ITCA indicates the combination of cell type 19 and cell type 30. Looking at the labels, we can actually see that the 2 cell types are indeed very similar. So Also, this is confirmed in the t-SNE plot by changing the hyperparameter, the perplexity. We can see that no matter how the resolution, the visualization changes, the two cell types 19 and 30 are always together. And looking at the gene expression heat map in the 40 principal components, we can also see that the two cell types are not that distinct compared to another two cell types we used for comparison. Finally, ITCA can guide the construction of a cell type hierarchy, and this is what we can do using ITCA for consecutive combination of classes into a tree versus the traditional hierarchical clustering. So roughly speaking, we can see that the ITCA will give us more balanced branches, and also it agrees better with our knowledge in terms of major cell type labels. So finally, I want to make a comment about the classification algorithm we should choose to work with ITCA. First, ITCA is adaptive to all algorithms, from random forest to neural networks to just the linear discriminant analysis. But it depends on the goal. If the goal is to do prediction, then a strong classification algorithm is clearly preferred. But if the goal is to detect similar classes to be combined, then actually a weak classification algorithm may be preferred because it can encourage combination. So finally, I want to thank my visiting student, Chihao Zhang from Chinese Academy of Sciences. So he visited me during the first year of pandemic, and we had this work together. And also his advisor in China, Dr. Shihua Zhang, and also my UCLA student Yiling for collaborating with Chihao. And our paper was published in Journal of Machine Learning Research. Thank you.